We've been talking about whether El Nino is affected by global warming, but there is another way to think about this. El Nino has all these teleconnections in all seasons into heat waves, floods, droughts, wildfires, health, etc. And there is global warming. When there is no El Nino, we are all talking about global warming, the extremes, and how global warming makes everything worse. But when El Nino comes, suddenly everybody stops talking about global warming. So, how is it that they're actually interacting with each other, and whether a new index is needed to now measure El Nino because El Nino is happening on top of global warming? So, the latter topic about new index we'll discuss in the next podcast. Here, let's just revisit the El Nino and La Nina teleconnections. Very nice pictures or schematics are given by NOAA and a lot of other operational centers, and now every media outlet makes its own schematic of how things work. But everybody is now forgetting that global warming is actually always there in the background, right? So here we are with the standard El Nino, La Nina perturbations. So during an El Nino, you have Indian Ocean doing something in terms of surface temperature patterns, and we have the standard cold horseshoe pattern anomaly and the warm anomaly here. And we said there are multiple patterns of warming, and this may be disappearing because there is strong global warming happening here. What does that mean for the coupling between the Indian Ocean and the Pacific Ocean? We don't know that, but nonetheless, when there is El Nino, we have normal conditions look more like this with strong deep convection over the western Pacific, 5 meters of rain per year. It's called the boiler box here, or the maritime continent, because of all the heating which drives basically lots of connections to global weather patterns. During an El Nino, the warm pool is displaced this way. We have talked in detail already. So you have the warm pattern here, cold pattern here. So you have sinking air, the Walker cell. This is the Walker cell here, has been displaced eastward. So deep convection is displaced eastward. You have downward subsidence happening on either side, and the Indian Ocean also has perturbations to its Walker cell and Hadley cell. So you have perturbations to deep convection on this side, West African monsoon, East African monsoon, and so on. And during a La Nina, you have exaggerated normal conditions. So you have colder than normal cold temperatures, maybe extending far eastward, crunched up warm pool with a horseshoe pattern again, and Indian Ocean has the opposite sense in its response. And remember that El Nino is this, you can think of as a mature pattern. El Nino evolves, decays, and then transitions to either a cold condition or a neutral condition. Sometimes El Nino continues in the second year, very few, but it happens. And during that time, you have various other teleconnections as well. For example, in the El Nino decaying phase, following the peak, you get a basin-wide warming here. During an El Nino, you often get cooling here and warming here, which we call IOD, Indian Ocean Dipole, but sometimes it's also known as the Indo-Pacific Tripole, and there is strong arguments to be made that they are strongly coupled because of this Walker cell, etc. So you have dry sinking air in these places, warmer than average temperatures, all these places, and cooler than average temperatures here, cooler than average, warmer than average, cooler than average, and sinking and rising motions, right? Amazonia with its own deep convection, etc., which gets suppressed during El Nino. All those things we have discussed. But in terms of teleconnections, if you had nothing else happening, typically this is how you would think of El Nino. So extended Pacific jet stream, amplified storm track. So you have warmer in the winter, especially you have wetter conditions here, drier conditions here, and we'll see that you have impacts here on the hurricane season as well. And sometimes you have also the polar jet stream together. They are funneling more water here. So especially lots of winter storms, at least used to happen. 97, 98 El Nino created real havoc here in the winter of end of 97 winter into 98 winter, and then there was a sudden transition to La Nina. So during La Nina, on the other hand, you have polar jet stream is way to the north, dipping here, causing wetter, colder, drier conditions here. So these are very well known in terms of their El Nino teleconnections, but you have to remember cold conditions here are also La Nina conditions. So these west coast of North and South America are typically very dry. Atacama Desert, all these Peru, Chile, into western states of the US, all the way from California into Oregon and Washington are all dry states climatologically. And the other thing to note is that El Nino and La Nina are not exactly symmetric in that sense. You can also see those here in the teleconnections. So these are the typical El Nino and rainfall. So El Nino conditions in the tropical Pacific are known to shift rainfall patterns in many different parts of the world. So they may vary somewhat from one El Nino to the next. So obviously we make a composite. The strongest shifts remain fairly consistent in the regions and seasons shown in the map below. We have already discussed how the dateline El Nino or Central Pacific El Nino is argued to cause more severe droughts here than the Central Pacific El Nino, and then we argue whether IOD decouples the Indian monsoon from the El Nino and so on. But nonetheless, you can see that the greenish colors are where wet anomalies occur, yellowish colors are where dry anomalies occur. So you have January to April wet conditions over here in central western Asia into Eurasia. The monsoon region, of course, gets drier during June to September. As we are sitting here in the beginning of July 2026, monsoon has been relatively dry. The deficits are reduced, I think, down to maybe 30% because heavy rain happened in the last few days, literally, and still large parts of the country are drier than normal. But you can see that January to April, the transition or evolution phase, you have maybe wetter region here, especially in October to December. So you have January to April and June to September. So there is a transition, and so spring months, and then so we are talking about the El Nino year, not the following year. So you have West African dryness happening, but East Africa gets wet during an El Nino. Remember, East Africa has two seasons. During the onset phase here, March, April, May, you get a short rainy season, I think, maybe longer rainy season, please check. And the retreat of the monsoon, of the Indian monsoon, we get another wet spell here. I think it's the short rainy season. So October to following January generally tends to be wet here, but November to March in southern Africa, you get drier. This is, of course, the standard shift of the Walker cell. June to following April, wet, Jan to May here, and you have dry pattern here. July to following April, June to following January, September to following March, July here, July to January, July to November. So do they occur this way every single El Nino? Of course not. Depends on the strength, the warming pattern, whether it's the warming is happening more here or here, and so on. But these are kind of the composites. So November to following March, dry here and dry here, December to March, wet in general from January to April. So it's more of a winter teleconnection that's following the peak of the El Nino into the following year. November to following April, and here Amazonian dry sinking we saw here during an El Nino that shows up here. You can see, and then there are smaller patches of wet June to September here, and September to following January wetness here. So you have the South Atlantic convergence zone going here, the Atlantic ITCZ going here. So all kinds of teleconnections happen. Just remember these, and then you have La Nina teleconnections, and you can see that that's not symmetric at all. So you do get some symmetric wet July to September here, dry July to September. You get dry here, but not as big as is the wet here, but you get shifted, but wet spell November to April. October to December is dry. Generally, La Nina brings some excess rain here. January to May dry on this region, which is wet and shifted during El Nino. This is horseshoe pattern is replaced by wet anomalies. Again, June to December, September to following January, May to following February, August to December. So not very symmetric, but this can be drier. So cold tongue is colder. Walker cell is more shifted to the west, so heavy rain over here, but dry June to following April here. I think I've lost power, so it's really hot in here. AC is not running anyway. I ran fans, but all the fans have stopped. So I'm in Kanpur. Very hot. It's been raining on and off, but as soon as the rain stops, it warms up like crazy and it's very humid. Okay, so continuing, typical El Nino influence, looking at the hurricane season, more hurricanes due to less vertical wind shear during an El Nino, but this is not working every time. Fewer hurricanes due to stronger vertical wind shear and trade winds and greater atmospheric stability here during El Nino, sorry. So this is typical El Nino influence. Oops, somebody has, cleaning people have left the music was on, so sorry about that. But anyway, coming back to here, during El Nino, you have fewer hurricanes and stronger vertical shear and trade winds and greater atmospheric stability. And here is where it's important to think, if North Atlantic is really warming a lot, can El Nino still do this? Not necessarily, so we'll have to see that. More hurricanes due to less vertical wind shear here, warm, wet here, as we know, warm pool is spread into this region. La Nina, you have more hurricanes due to weaker vertical shear and trade winds and less atmospheric stability on the Atlantic side, fewer hurricanes due to stronger vertical shear here, cool and dry here. So these are what you would expect, and we have this kind of a pattern built over 50 years or longer by compositing all the El Niños and La Niñas that have happened. But now there is all this rapid warming in some hotspots. So this is warming much less than other regions, especially compared to the Western Pacific. And this is warming much more Atlantic. And there are other patterns happening here, as we will see in a minute, which is what this is. So this is the warming pattern from November. Oops, power is gone again, 1901 to 2024. But if you look at more recent period, 1994 to 2024, there are warming hotspots over the Western Asian, Middle East and Mediterranean region. Europe is warming very fast. There is of course the Arctic amplification. We have discussed it elsewhere. There is a warming hole here in the North Atlantic related to AMOC and various other things. This is warming less or even cooling, which produces positive feedback because you have warming on the western side, cooling here, which means SST gradient is getting stronger. So you have a wind feedback, and the debate about whether global warming will be like an El Nino or a La Nina continues. Richard Seeger had predicted in the early 2000s that the warming pattern will continue to produce cooling here, and he has been looking at all the models, and models generally fail to reproduce this. If it cools here, ocean can take up more heat and actually can modulate global warming. That's on a low frequency, long time scale, trend scale. But during a La Nina, during an El Nino, of course, heat gets released from the oceans. We have a mini global warming which superposes on top of again I have music coming on. I have to see if there is a bug in the system that when power goes off, it starts kicking in. Nonetheless, you get the idea that now we cannot talk about El Nino and La Nina and the teleconnections without worrying about the background warming that is not disappearing. Look at 2026 June. Global sea surface temperature anomalies. El Nino is, of course, happening here, looking very strong, but you have the specific meridional more kind of pattern, and you have incredible warming going on here in the North Pacific with a very clear feature of the Kuroshio extension. You have to be careful with these western boundary fronts because if you shift it, it can look warmer or cooler depending on which way you shift it. So they are not necessarily anomalies in the same sense as here. Here you have in situ warming, whereas here you have a shift. But these are real, and there are associated pressure patterns here. You can see the Arctic is really hot. North Pacific has this kind of a tripole pattern. Cooling here still continues. Warming again, the Gulf Stream front is here as well, and all these other signals. So you can imagine that the teleconnections from El Nino are not completely independent of these background warmings that are happening. These are not El Nino related warming patterns. Some of it may be, like the Indian Ocean, for example, but rest of them are unrelated and could be global warming, or many of them are global warming patterns. So any teleconnections and even an index for El Nino now may have to include these tropic-wide warmings. And that's what we will look at in the next podcast, where ECMWF is working with WMO to produce a new relative it's called relative ONI, Oceanic Nino Index, relative to the tropical warming. So there is a way of taking the anomaly of the tropics-wide warming and measure El Nino with respect to that, because otherwise El Nino is looking stronger than it actually is because of the background warming. Okay, this is why I wanted to revisit the teleconnections and global warming together. So we'll come back and look at that. Sorry about the interruptions because of the power, but this is what life is like in India. Power interruptions are very common. So let's leave this here, and then we'll look at the relative Oceanic Nino Index, or RONI, in the next podcast. Okay.